Welcome to the video key for quiz 1. So in the first question, we're looking at interactions between a propane molecule and a propanol molecule. So we've got let's put them a little closer together. So we've got a propane molecule and we've got a 2-propanol molecule. Okay, we want to know their IMFs. Okay, well clearly we're always going to have London dispersion, so let's just circle that to start. What about the other ones? So to have dipole-dipole, we need to have both molecules be polar. Well, if we look at this one, surely there's going to be a dipole moment. And I haven't drawn the implicit hydrogen here, but we know that in general it's going to be something like that. We're going to have a dipole moment towards the oxygen, right? That both the carbon center but also this hydrogen are going to have partial positive charges because the oxygen is so electronegative, so we have a partial negative charge on that oxygen. On the other hand, if we look at propane, it's a hydrocarbon and we know that that doesn't have any a very modest amount of separation of charge, and it's not going to have a dipole moment. So we can't have dipole-dipole, so let's cross that off. Dipole-induced dipole. To have dipole-induced dipole, you need to have at least one of the molecules be polar, but not necessarily, you don't need to have both, just at least one of them, right? So that's saying that this dipole can induce a dipole in the other molecule. So we have a permanent dipole moment here, and that's going to tend to, if we, actually the lineup is not exactly right, but if we imagine pointing this dipole towards this molecule, then that's going to distort the electron cloud in the other molecule and sort of push electrons over here, leaving behind a temporary dipole moment like that. So a dipole can induce a dipole, so certainly we could have dipole-induced dipole. Hydrogen bonding. Well, we have one molecule with a hydrogen bond donor atom, a hydrogen bond acceptor atom. Okay, so this one's ready. The question is, can it have an interaction with a propane molecule that's hydrogen bonding interaction? No. Because although there are all hydrogens on this molecule, we know we can draw some of them in. We can see that these hydrogens are not directly bonded to an oxygen, fluorine, or nitrogen, so they're not hydrogen bond donors. They can't be the other end of a hydrogen bond donor, of a hydrogen bond. So we can't make a hydrogen bond between these, so let's cross that off. And then ion-induced dipole, we'd have to have an ion and then something for it, a second molecule it could do. So as long as there's an ion present, we will have ion-induced dipole, but we don't have any ions here, so we can cross that one off. So it's B and D. All right, we mix water at 100 degrees C with water vapor at 150 degrees C. And we want to find the final temperature. Which parameters do we need? So one way to think about this is to do one of these temperature versus heating curves, and we'll draw the first one, we'll just draw a general one in red, and then we'll go over it to see which segments we need. So we can imagine heating up a solid, and then melting the solid, and then heating up a liquid, and then melting, and then boiling that liquid, and then heating up the vapor. So in principle, we could have, gas, and we could have liquid, and we could have solid. So here we have melting, and here we have boiling. So there's all these different terms that in principle we could have, but where are we in this specific problem? Well, we have water at 100 degrees C. So it's liquid, but it's at 100 degrees C. So that means we're in this liquid segment, but we're at the top. So we're starting here. Okay, there's the water. And we have water vapor at 150. So we're not at the boiling point, right? So if we could label this as being TB, the boiling point, and this would be TM, the melting point. So for the water vapor, we're not here at the boiling point, we're at some higher temperature. So let's put up here. So we can see that the hotter thing is going to lose heat to the colder thing, and it's going to cause it to boil. But notice that we're not going to need any of the other segments, and so we could sort of just maybe circle the stuff that's relevant. I'll circle that here. We're going to, this is the only part of the heating curve that's relevant. So what that means is we don't have any kind of heating up the liquid term, right? We can't heat the liquid up. It's already in 100. So the only thing that's going to happen to it if we put heat into it is its temperature is not going to change, but it's going to go through a phase change to become gas. Okay, so we don't use the specific heat of water if we're once we get to 100 degrees, we don't need it, right? We can only use that if we want to heat water between some temperature between 0 and 100. Okay, so once you get to 100, you're done with that term. So we're already 100, we don't need specific heat of water. So let's cross that off. What about the water vapor? Yes, because look what we're doing. We're taking the water vapor that's on 150, and once we put it in contact with that water that's only at 100, that's colder than 150, so it's going to lose some heat. So we definitely need the specific heat of water vapor. What about the heat of fusion? Well, that's way down here, and that's not part of our analysis, right? There's no way we're going to be able to freeze any water, so we don't need that. And so these arrows moving towards each other represent the part of the system that's gaining heat and the part that's losing heat. So we can't go outside those bounds. We can't end up higher than 150 or lower than 100 because we have to. Those two things are, one's going to lose heat, one's going to gain heat. They're going to move towards each other. Okay. What about the heat of vaporization? Well, notice if we put any heat at all into water at 100, it's going to boil. So we do need the heat of vaporization. Specific heat of ice. No, see that's way down here. That's this, right? That would be if we had ice below 0 and we need to heat it up. We don't need that. So let's cross that off. So the correct answer here would be B and D. So if you just put one of those, you got partial credit. Okay, so here we have a question, and let's go ahead and write the reaction. So we're going to mix acid, and we're going to mix it with a base. They're both aqueous, and since we have a strong acid and a strong base, then we know the hydrogen ion reacts with the hydroxide ion to give us water, and the leftover bits give us aqueous salts. So we're going to have lithium nitrate aqueous. Okay, so the question is, and these acids and bases were both aqueous, so put a little note on them saying that they were aqueous. Okay, so the question is, what happens if we do this at different length scales? Okay, how does that affect delta T? Well, if we think about this, what we're doing here is we're cutting the volumes in half. Okay, so notice there's not a limiting reactant here, right? We're using equal amounts of the acid and base, and the concentrations are equal, right? So that means we need to supply these in a 1-to-1 molar ratio, and we are, because the concentration and volumes are the same. Okay, so what happens if I cut the volume of acid in half and we cut the volume of base in half? So we're still going to have a 1-to-1 ratio of moles to moles, but we're going to have fewer, right? So Q reaction is going to go down by a factor of 2. And you might think, oh, that means a smaller temperature increase. But we've got to remember something here, that the specific heat, or I shouldn't say the specific heat, but the heat capacity is equal to the mass times the specific heat. And notice that the mass went down by a factor of 2. So this, and the specific heat of water, of course, doesn't change. So that means that this went down by a factor of 2. And why does that matter? Well, the heat capacity is how hard it is to change the temperature, right? So the more stuff you have, the harder it is to change the temperature, the less stuff, the easier. So you cut the amount of heat you put in to the water by a factor of 2, but now there's half as much water. So those two factors are going to cancel. And if we wanted to, we could really be formal about this and say, the Q of reaction, in this case, it's going to be the moles of acid times the heat of reaction. And we could, the moles, I'll just leave it like this. And delta T, or Q for the water, is equal to M water, C water, delta T water. And if we add up Q reaction and Q water, they have to equal to 0. And so we can say, the Q reaction is equal to the negative of Q water. We can plug in those variables here. So we've got N acid times delta H of reaction is equal to the negative of MW CW delta T. And we solve for delta T. So if we solve for delta T, we get N acid delta H of reaction divided by the mass of water divided by the specific heat of water. And notice that we took the moles of acid and we cut it in two. We took the mass of water and we cut it by a factor of 2. So this went down by a factor of 2, and this went down by a factor of 2, and those are going to both cancel, right? And so now our delta T is unchanged. So we have the same temperature increase. So you can figure this out just using sort of logic, or you can actually do the equation. Either way will give you the same answer. Okay, number 4. Number 4, we're imagining a cup, and we've got some ice. Let's just call this ice instead of drawing it. And then we've got acid, and we've got base. And it doesn't matter what order we put it in, because the mass of ice is a state function. So whether we mix this and add the ice, or add the ice and then mix it, either way it's the same. And the important thing here is the solutions are at 0 degrees C, and the ice was at 0 degrees C. So that means that really we don't have, and we know that not all the ice melts, right? We have excess ice. So all that's going to happen is some of the ice is going to melt because this reaction has a heat associated with it. So we can say Q reaction plus Q ice melt is equal to 0. Well, now we can't just solve it like this. We got to put in the symbols from the problem, right? So Q reaction. Well, let's write the reaction up. The reaction's written out for us. We can see this is also going to be a 1-to-1 stoichiometry, and we're given additional information. The final pH is neutral. What does that mean? That means we didn't have leftover acid or base, right? And if there's no leftover acid or base, that means neither one of those chemicals was in excess, right? They were both eaten up by the reaction, which means that we don't have to worry about like one of them is limiting and we have excess on the other. So since neither one is limiting, or actually equivalently they're both limiting in the same way, we could calculate this based on acid or base. So it'd be perfectly right to write this for base or acid. But I could say the moles of acid times the heat of the reaction, that's going to be the Q reaction, right? Because there's one, this number delta H here is the number of joules or kilojoules per 1 mole of perchloric acid. Or equivalently, I could have done the same thing with base, right? Because they both have a coefficient of 1. I could say NB times delta H reaction gives us me the heat of the reaction. Okay, with ice melting. Well, now it's the moles of ice. We have to be careful. We don't mean the total moles of ice, right? So we could have a kind of a clunky name here and say ice that melts, just to remind ourselves. We can shorten this later, but just call it N-ice, but we put that in parentheses. So if we multiply that times the heat of fusion, that is going to give us the Q for the ice melting. Okay, and so those are only sources of heat, so they go to 0. We're not done yet though, because N melted, or N ice melted, is what we're solving for. So we think we could solve for this. Let's go ahead and solve it like this. So we've got Na delta H is equal to negative N. I guess N melted is just as good as name, times delta H of fusion, and these are all standard heats of fusion and standard heat of reaction. So I got to solve for N melted. So N melted, I'm going to divide both sides by the heat of fusion and also divide by -1. So I get negative NA delta H over delta H of fusion. Okay, now we have to be careful. The moles of acid was not a symbol that was given, right? So we're going to have to come up with a better answer than moles of acid. So if we have the concentration of acid and we have the volume of acid, we know that that's moles per liter, and or concentrations moles per liter, and we can convert mils to liters. So if we multiply concentration times volume, we can get our moles. So we could say the concentration of acid times the mils of acid divided by 1,000, right? Because we want to convert mils to liters. That's going to be the same as moles of acid. And then we've got our heat of reaction over our heat of fusion. Okay, now there's two things we can do with this answer, and we should do both of them. Because I didn't say what units I put the heat of reaction in, I gave full credit whether or not you had the 1,000 there. Okay, if I had said kilojoules though, you'd have to put that in, put this factor 1,000 in. So let's see why. So if I put the units in, I've got concentration in molarity, which is same as moles per liter. I've got mils, and then I have 1,000 mils for every liter. That's 1,000 down there. And then I've got the heat of fusion, that's in kilojoules. Oops, that's down here. So heat of fusion is kilojoules per mole, heat of reaction kilojoules per mole. So these cancel, my mils cancel, my liters cancel, and I'm left with units of moles, and that's what I wanted. We're not done yet though. Before we plug the numbers in, let's see if this makes sense conceptually. Okay, we're looking for how much ice melts. According to our formula here, this would be our final answer. Notice we're saying that if you've got a bigger heat of reaction, right, if the acid and base give off a lot of heat that's on top, that means you're going to melt a lot of ice. Okay, that makes sense. On the other hand, if it takes a lot of heat to melt the ice per mole, the bigger that number is, the less ice is going to melt. Okay, that makes sense too, right? So the bigger this number, the smaller the N melted, right? So if it took 1 billion joules to melt a mole of ice, we would hardly melt any ice at all, right? Okay, what about this other part, this concentration times volume part? Well, the more concentration of acid and the more concentration and the more volume of acid, as long as we balanced it with base, which we said we did, the more ice we're going to melt. So that makes sense. So stop and look and see if like what's on top and bottom makes sense. Because notice if we switch delta H and delta R, the units are still going to work out. But this thing of like, oh wait, the more heat the reaction gives off, the more ice should melt, that's going to tell you that that should be on top and the other one should be on the bottom. So you want to go through that logic after you've done your algebra, and if the logic doesn't seem to make sense, go back and check your algebra. Because some of you had these delta H's flipped, and that's why. And that concludes the video key for quiz 1. Thank you for watching.